Hello, everyone. So last time we finished chapter 1 from the book. Now we want to start chapter 2. Chapter 2 is about basically set theory. Set theory. Now let's start with 2.1, which is about sets. And we want to start with the definition of set. So what is a set? So a set is any collection. So let me say any unordered collection of objects. So, and the notation is basically, let's say this notation, and we put the elements inside this notation, curly bracket, right? And these are going to be called the elements. Elements of a set. And normally we use capital letters to denote sets. So capital A, capital B, capital C, right? So let's look at an example. Let's say we can talk about, let's say, the set of students in math, let's say 120 flex section in summer 2021, right? So I can say, for example, capital A equals, and then I can write down the name of students in our class. Let's say student 1, student 2, student 3, and I separate them with a comma, right? And I can include all the students here. Okay, or for example, let's say the set of, let's say odd numbers, which are positive and let's say less than 10. So what is the set of odd numbers which are positive and less than 10? Let's say capital B equals 1, 3, 5, 7, 9, let's say, right? So we can talk about this set. And there's always also a set builder notation that we can use, right? So set builder notation. Usually, we describe the set builder notation as, let's say, A equals. So we use this is for set notation. And then we describe the elements, right? So X belongs to some set. Let's say B, and then we write this notation, which means such that. Read such that. And then we describe the elements. So for example, let's say rational numbers. We can say that it's the set of elements X, let's say in R, such that X is equal to M over N for some integers M and N, with N not equal to 0. Okay, so and important sets that we have in mathematics, important sets. And the notation, n is used for natural numbers. And natural numbers in some books, they start with 1, 1, 2, 3, 4, all the way to infinity, but some books start with 0. So your book starts with 0. So 0, 1, 2, 3. This is the set of natural numbers. And then we can talk about Z, the set of integers. What is the set of integers? 0, 1, 2, 3, and also -1, -2. So this one is the set of integers. And then Q is for rational numbers. We defined above, right? And also R, the set of real numbers. Okay. Now, the next thing we have to do and we have to define is, when can we say that a set is a subset of another? So subsets. So let's assume we have two sets, let's say capital A and capital B. When can we say that? Let's say capital A is a subset of capital B. So given two sets A and B, we say that A is a subset of B. Subset of B denoted by, so the notation is like this. If for every X, if X belongs to A, then X also belongs to B. Okay, so in other words, if every element of A is also an element of B, then we say that A is a subset of B. But if at least one element of A is not in B, then A will not be a subset of B. So let's look at an example. Let's say if I define, let's say A equals, let's say 1, 3, 5, and B equals 1, 3, 5, 6, 7, then A is a subset of B, right? Because every element of A is element of B as well. 1 is in B, 3 is in B, 5 is also in B. So another example, let's say A equals 1, 3, 5, and then let's define another set. C equals, let's say 1, 3, 4, right? Then A is not a subset of C, since 5 belongs to A and 5 does not belong to C. So if you can find at least one element of A, which is not an element of C, then in that situation, we would say A is not a subset of C. Now, what about equality of two sets? Equality. So we given again two sets, A and B. We say A equals B if A is a subset of B and B is a subset of A. So if A is a subset of B and B is a subset of A, then we can say that A and B are equal. Otherwise, if A is not a subset of B, or if B is not a subset of A, in any of those situations, we would say A is not equal to B. Okay, so for example, let's say A equals 135, B equals 1356. Now in this situation here, A is a subset of B, and B, however, is not a subset of A, right? Every element of A is in B, but not every element in B is in A, because 6 is in B and 6 is not in A. So since one is subset of the other, but the B is not subset of A, we can conclude that A and B are not equal. Okay, so another thing we want to look at, a null set or empty set denoted by phi is a set containing no element. Set containing no element is called null set or empty set. Now, important property of this null set or empty set is that empty set is a subset of A for every set A. Why can we say that the empty set is a subset of every set in the world? So the reason is that, or proof. So when do we say, whenever you want to prove a statement in mathematics, first you have to think about the definition. So when do we say, what is the definition of subset? When do we say that a set is subset of another set? If for every x belongs to the first set, implies that x belongs to x belongs to the second set. So we need to show that for every x belongs to phi, implies that x belongs to A. Now x belongs to phi, so see we have a conditional statement here. P implies Q. What is P? What is the hypothesis or assumption? Now assumption is x belongs to phi, which is false, right? By definition of phi. Phi is a set with no element, right? So x belongs to phi is false for every x. And we know that false implies anything is always true, right? Which is false. Thus, so let me call this one star maybe, or 1. Thus 1 above is true. Since false implies true. False implies any statement, basically. False implies false, and false implies true are both true, right? So whenever the hypothesis is false, the whole conditional statement is going to be true, no matter whether the conclusion is true or false. So this is what we have learned in the first chapter, right? P implies Q is true as long as P is false, no matter whether Q is true or false. Okay. Now, we want to also look at the Venn diagram. So Venn diagram. Venn diagrams. So this is a diagram to get some intuition about sets and their properties. Normally, each set, normally in this type of diagram, each set is represented by a circle. So let's say this is A and this is set B, right? So this is, in general, if you have two sets A and B, then we can denote them using Venn diagram this way. So this is two arbitrary sets A and B. But let's say if you have, for example, A, you know that let's say A is a subset of B already. Then A would be like this, B would be like this. So here, A is a subset of B. Because A is a subset of B means what? Means every element of A is inside B. So that's why if you want to represent with circles, we would put A as a circle inside B. So to show that every element of A is inside B. Okay, then another notion you want to look at is cardinality of a set. Cardinality of a set. So basically, cardinality means the number of elements. Number of elements. Now, if A is a finite set, meaning if it has finitely many elements, it's very easy to define cardinality or number of sets, right? So if A has n elements, naturally we would say that cardinality of A, or the number of elements in A, is n. Okay. So definition, if A is a set with n elements, then we say that the cardinality of A is n. And the notation that we use, sometimes we use card S, or sometimes we use like this absolute value sign. So another definition, if cardinality of S is equal to n for some positive integer n, for some positive integer n, then we say that S is a finite set. Finite set means cardinality is a positive integer. Otherwise, we say S is an infinite set. Infinite set. Okay, so for example, if let's say S is equal to N, the set of natural numbers, then S is an infinite set. Why is natural numbers infinite set? Because the cardinality of natural numbers is not equal to any positive integer. It's not equal to 5, it's not equal to 10, right? The cardinality means the number of elements. It's not 5, it's not 10, it's not any positive integer. So we say that natural numbers is an infinite set. Now, one important remark here is that cardinality can be defined for infinite sets which is one of the main purposes, one of the main goals of this chapter is to define and compare a cardinality of infinite sets. So you may tell me, okay, well, this looks easy. We can say that cardinality of an infinite set, we can define it as infinity, let's say. Well, yes, that's a straightforward idea. But then we will have one issue, and that is, what about if we have two infinite sets? If we define the cardinality of any infinite set to be equal to infinity, then any two infinite sets would have same cardinality, which is not what we want. We want to have a better or more precise comparison. We want to have a tool to compare the number of elements in two infinite sets. We don't want to just say that all of them are infinity. For example, we will see that real numbers and natural numbers are both infinite sets, but cardinality of real numbers is bigger than cardinality of natural numbers. But interestingly, for example, natural numbers and set of integers, they both are infinite sets, and it seems that maybe we should say that set of integers has bigger cardinality, but we will see that no, that's not the case. Set of integers and natural numbers have exactly same cardinality. But real numbers have bigger kind of cardinality compared to these two sets. So these are the things that we are going to define later, and we are going to develop tools and definitions to be able to compare, two infinite sets. Okay, so that's what we are going to do later. For now, we are just doing some basic definitions related to sets. Okay, and then the next notion we want to look at is power sets. So power sets. So what is a power set? So definition. Given a set A, we call the set of all subsets of A as, we call this as the power set of A. Power set of A denoted by P of A. So like this curly P of A means the set of all subsets of A, and it's called power set of. Okay, so let's look at a simple example. Let's say A equals, for example, 1, 2, 3. Find P of A, power set of A. How do we find the power set of A? Power set by definition, we have to look at the definition, of course. What is the definition? Power set of a set is the set of all subsets of that set. So first, if I want to find the power set, first I need all subsets of A. So what are the all subsets of A? So first, we need all subsets of A. So what are they? So here they are. So the first subset is phi, or empty set. We saw that phi, or empty set, is a subset of every set in the world. Therefore, it's also a subset of A. What else? Let's say, for example, the set containing only 1, right, is a subset of A. What else? Only 2. Only 3. What else is a subset of A? 1 and 2, for example. 1 and 2. 1 and 3. 2 and 3. And one more, right? What else is a subset of A? So write 8 here. I can write maybe down. The whole A, 1, 2, 3. The whole A is also a subset of A. So A is a subset of A for every set A, right? So whenever you have a set A, we can say A is a subset of A. Why? Because every element of A is, of course, in A, right? How do we show a set is subset of another? We have to show every element in the first set is also in the second set. Now the first set and second set are both A. So every element in A, of course, is in A. So that means every set is subset of itself. So thus P of A, the power set would be, what would be the power set? The set of, please remember, the set of all subsets of A. So here I have 8 subsets, right? So the set containing these 8 subsets would be called power set, the set of all subsets of A. So the set containing these 8 subsets is going to be called power set. So set, so because it's set of, so I have to use the set notation. Then I have to include all these subsets, all these 8 subsets, so which are going to be phi, and then the next one is going to be 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, and 1 and 2 and 3. So how many elements does A have? So I can add part B to this. Part B, find a cardinality of power set of A. So cardinality means number of elements. How many elements does P of A have? Let's count them. So this is the first element, and then there is a comma. Then this is second, third, fourth, fifth, sixth, seven, 8. So 8 elements. The cardinality of P of A is equal to 8. Because P of A has 8 elements. Now another part, let's say, is 1 now let me write this way. So does 1 belong to P of A? So this is the notation for element of, right? So does 1 belong to P of A? Or in other words, is 1 an element of P of A? Yes or no? 1. So when you want to see if something is element of a set or no, you have to look at your set. Does that element appear here? So see, this is the first element of P of A. This is second element of P of A. This is the third element of P of A. So this element appears, right? So this is an element of P of A. So the answer is yes. 1 appears as an element of P of A. Now another part, if we say is, for example, 1, is 1 belong to P of A? Is 1 an element of P of A? Here I said does, but I guess it does this belong to, or does 1 belong to P of A, or is 1 an element of P of A? What about this one? 1 belongs to P of A. Well, we have to, if you want to know something is element of a set or no, we have to look at that element, that set. Does that element appear exactly as it is asked inside my set? Well, my element, how do I know my elements? Remember, each element is separated from other elements by a common comma sign. So this is the first element, then comma, then this is second. So this is my second element, then comma, this is my third element, and so on. So my second element is this set, this element, which is a set of 1. Now, tell me, do you see this one appeared inside my this set? No, not as exactly as it is. Yes, the set containing 1 is inside P of A, but 1 is not inside P of A. The answer is no. 1 appears as an element of P of A, but not 1. Part E is a 1 a subset of P of A. What about this one? Is 1 a subset of P of A? What do you think? It will show you P of A again. This is P of A. Is 1 a subset here? The set containing 1, a subset of this. Well, we have to think about the definition of subset again. When do we say that a set is subset of another set? If every element inside the first set is also an element inside the second set. Now I have two sets here. In the left-hand side, I have a set containing 1. I have to check whether every element inside the first set is it also inside the second set. Now, but my first set has only one element, which is 1, number 1. Now, is 1, number 1, an element of P of A? We saw in the previous part that the answer is no. So the answer to this is no, because 1 is an element of 1, but 1 does not belong to P of A. See part D above. Every element in the left-hand side should be an element in the right-hand side. The left-hand side, the set inside in the set appear in the left-hand side is a set with only one element, and that one element is number 1. Now, is number 1 an element inside the right-hand side? The set appeared in the right-hand side. Number 1 is not an element of the right-hand side set. This is what we established in part D. Right? So if number 1, which is the only element inside the left-hand side set, is not in the right-hand side set, well, that means this set is not a subset of P of A. Now, how can I make it a subset of P of A? Do you have any suggestions or ideas? Think about it. I can modify this a little so that the answer becomes yes. Is 1. So the set containing the set of 1, a subset of P of A. Now the answer is yes. Why? Again, we have to think about how do we show that a set is subset of another set. We have to show that every element inside the first set is also in the right set. Now the left set has only again one element. What is the one element? So since this set has only one element, what is it? Namely, so this is the set of which element? This is set with only one element, because it's only one element because there is no comma, right? Remember, we separate the elements with comma between them. This has no comma, so there's only one element, and that one element is set containing 1, right? This set has only one element, which is the set containing 1. And now this is the only element of the left-hand side. Is this element in the right-hand side as well? Which is in the set in the right-hand side, which is P of A. Why is it? Well, we already established here, part C. Look at part C. We established that the set containing 1 is an element of P of A. And that's exactly what we want to use here. The set containing 1 is inside, as an element, is inside P of A. So C, part C above. Okay, what else can we ask? G is, let's say, does, because previous ones I said does 1 belong to A? What about A itself? So far we talked about P of A, which is a little bit more confusing compared to A, because P of A is the set whose elements are subsets of A. That's a little bit confusing for some students, because they used to encounter with sets whose elements are numbers, right? But power set is a set whose elements are sets themselves. A set, the set of all subsets of A. So the elements of power set are sets themselves. Which sets? Subsets of A. So that's where it's a little bit confusing. But for A, it's straightforward. Does 1 belong to A? How do we know? We have to look at A. Here's A. And then we have to see whether that element appears in A exactly as it is. Well, look at the first element, it's 1. Then comma means separated with the second element is 2, third element is 3. So first element is 1. Is it exactly as it is asked? Yes, 1 is also here asking about 1. So the answer is yes. 1 appears as an element of A. Part H is, let's say, the set containing 1, a subset of A. This one, the answer is yes. Because how do we know a set is subset of another? We have to check the elements in the left-hand side. Left-hand side set has only 1 element. So the set 1 has only 1 element, which is what? Namely 1, which is in the right-hand side set, which is in A. So that means 1 is a subset of A. Because in part G, we established that the only element 1 is in A. So that means the set containing 1 is a subset of A. So we saw that, with only this simple example, A equals 1, 2, 3, and P of A, we could ask so many questions. Some of them are a little bit confusing. Again, you have to do some practice about power set. It's a new concept, right? New concept, a set whose elements are not numbers, are sets themselves. We have similar ideas in mathematics. For example, for functions, normally, we used to see, for example, the inputs and outputs of a function to be numbers again. But in more advanced mathematics, we have some types of a function called functionals, basically, whose inputs are functions themselves, not numbers. So this is, I can say, a similar idea. It's a set whose elements are not numbers, are sets themselves. Okay.